There you go. It's working. Thank you. Well, I'll get started. So my verses for the day are from Proverbs this time. Proverbs 26, verses 4 and 5. They go as follows. Do not answer a fool according to his folly, or you will also be like him. And verse 5. Answer a fool as his folly deserves, that he not be wise in his own eyes. These are both very relevant to the world we live in. Just saying. I'll begin with a word of prayer. Dear Father, we thank you for this day and thank you for this class. Just ask you to be with us, help us to glorify what we do, and just to understand a little bit more about conservation, energy, and physics and all these things, Lord. In your name I pray, Lord Jesus. Amen. All right, so one of the things I have not talked yet about is if you have the net force is equal to, say, a sum of forces, F1 plus F2. And let's just, why not have n of them? If we're going to do 2, we might as well do n. Suppose you got n forces, right? How's the work calculated? Then, if we calculate the work done along some physical trajectory c, right? Then it turns out that we can break that up into the work done by the first force plus the work done by the second force plus the work done by the nth force. So this is the net work done. This would give us work done by F1. This would be the work done by F2. This would be the work done by the nth force. So this is interesting because we know that the work done by the net force is equal to what by the work energy theorem? So I could say this, work net is equal to the work done from the first force plus the work done from the second force, work done by the nth force, and this is all equal to the change in the kinetic energy, right? That was the work energy theorem. The interesting thing here is that, if one of these forces is conservative, then you can use that the work done by that force is equal to the minus the change in the potential energy for that conservative force, right? Here you go. So like application. If you had the net force is equal to like the force of friction, let's say, plus a conservative force, all right? And let's suppose that the conservative force in particular is equal to minus the change in the potential energy for that conservative force, right? Minus the gradient of u. In this situation, we'd have that the change in kinetic energy would be equal to the work done by friction minus the change in the potential energy in this situation. And so in particular, this would give you the equation like, KEF minus KEI is equal to the work done by friction minus the final potential energy minus the initial potential energy, all right? Which from this we could derive that the kinetic energy final plus the potential energy final is equal to the work done by friction plus what? Plus the kinetic energy initial plus the potential energy initial. So the story goes. Now, oftentimes I would write this in the other way. A lot of times I understand this principle in a problem as like the kinetic energy initial plus the potential energy initial is equal to the final kinetic energy plus the final potential energy minus the work done by friction. A lot of times I look at it like that, right? In other words, you're losing energy. Friction takes away energy, right? So, did I do that right? Just algebra. Okay. So let's look at some examples that involve this idea. So anyway, the big idea here is that the net work is the sum of the works done by each of the constitutive forces, you know? So example 1 here. Actually, let's start out with something a little bit simple. Let's start out with a really, really simple example. Suppose you got a box, right? Mass M. And let's say that the mass is 10 kilograms, all right? And Mr. Top Hat takes the box and he lifts it from here up to here, all right? Okay? So he somehow lifts this box from there to there. And he lifts the box in such a way that it goes from starting at rest, right? And so let's see here. To start with, we'll just say he, up here, it has a velocity upwards of what? What do you want to give it? Directly upwards. We have a choice. I have a 10 meters per second and a 5 meters per second. I'll make it 7.5. 7.5. I hear the people. There you go. I've taken the average. No one's happy. All right, very good. So the question, we can ask a bunch of different questions now. In this process of lifting the box of mass 10 kilograms from a rest on the ground up to what height do we want to make this? Well, this is about double my real height, so that would be 4 meters. Okay, now don't ask me how Mr. Top Hat lifted it to 4 meters. He's Mr. Fantastic. His stretchy arms. There we go. Thank you. So he lifts it 4 meters, and then at that top of that 4 meters, the box is going up with a speed of 7.5 meters per second vertically. So we can ask a number of questions about this process. So here's some questions that I would ask. Question 1. What work is done on box by gravity under this motion? Question number 2. What work is done by Mr. Top Hat during the motion? All right. Question 3. If F naught is the constant force applied by Mr. Top Hat, then what is F naught exactly? All right. So how should we solve this problem? What's going on? Well, first of all, energy is not conserved here, right? Energy is not conserved because, well, not unless energy is always conserved if you enlarge your system to take into account the exchange of energy between different bodies. But if we just think about the mass in and of itself, there's energy flowing into that system from Mr. Top Hat. It's lifting force, all right? So we can say this, though. The work done by gravity, right, plus the work done by, Mr. Top Hat, which I'm getting tired of. Let's just say Top Hat. Wait a minute. What am I doing? There we go. The work done by Mr. Top Hat That must equal what? So there's no friction, right? That's it. There's just the work of Mr. Top Hat lifting the box and gravity. That's all. Yeah, that has to be equal to the change in the kinetic energy. Very good. So which is 1/2. False praise is the best kind of praise. Let's see here. 1/2 mv squared minus 1/2 mv naught squared. It is always awkward when I see like students ganging up on some other student in a class and like, I don't know, this happened last semester. I was in some class and this kid said something really dumb, and then there were other kids in the class who just made him small, and like I couldn't think of anything to like help him out. I just felt so horrible, you know.
Character development.
Yeah, I guess he's life lessons learned, I suppose. Okay, so this is the work energy theorem. This is basically what we can use to understand the problem. It's at rest to start with, right? So we already know this is 0, right? And we can put a number here if we want. What is the net energy, the net change in kinetic energy here equal to? We work it out. What do we got? 10 kilograms times what? Times 1/2 times, by your choice, 7.5 squared. That gives us 281.25 newtons. Wait a minute, is that right?
That's correct.
That is not correct. You're looking for a joule. A joule. A joule is a Newton meter. Joule is equal to Newton meter. Now, there's another professor, well, let me shut up. I have seen people distinguish between joule and Newton meter, but I do not make such a distinction. To me, joule is equal to Newton meter because it is literally a Newton times a meter. But some people feel like you should give units of torque, for example, as Newton meters because it's more close to the definition of torque, which is R cross F. All in good time. Are there CFAWs here? Oh, why there's so many better choices. Why would you come to this class? Okay, well, welcome. All right. Let's see here. You're not like one of my students like punking me right now, are you? Okay, just checking. I mean, I know who all of you are, of course.
Yeah. Sir, you cannot not identify. I can never be framed for crime, but also
Well,
So give my handprint.
I guess, on the other hand, someone could frame you for a crime, but they'd have to put, they'd have to plan ahead. They would, and then you would be stuck in the position of being like, no, it was some other person like me, and then no one would believe you, and then you'd be in trouble. Oh, really? Yeah, well, see.
Yeah.
Hopefully they're not a murderer. Let's see here. So, let's see here. All right. Before let me stop working and getting fired. Let's see here. So 281.25 joules is the net change in kinetic energy. What is the work done by gravity? How do we figure that out? What's the work done by gravity here? So we want what? Yeah, just force, which is what? mg. And then times what? The distance, which is 4 meters. Now, is that right? Because what's the situation here? The displacement is like this, right? The force of gravity is like that, right? So technically, since it's a constant gravity, we're assuming we're near the surface of the Earth, so the force of gravity is constant. I know you guys are sad that we're not doing the integration that's required there, but to get it exactly correct, but you'll forgive me. So the dot product will do. The dot product of the force of gravity with the displacement gives us the work done, but that is just minus mg times 4 meters here, right? So what's that give us? Minus 10 kilograms times what? Times 9.8 meters per second squared times the 4 meters. What do we get? This one's dead to me. Rats. Thank you. Thank you for the assist.
Negative 392.
Negative what?
Negative 392 joules.
Negative 392 joules. Very good. That makes sense. The work of gravity is negative, right? In this motion. So what does that mean? So that's the answer to question 1. The work done by gravity is minus 392 joules. What's the work done by Mr. Top Hat during this motion?
It's work done by gravity plus the depth change. That's 281.25.
Ah, so solve for work Top Hat, right? Work Top Hat equals 281.25 joules minus the work done by gravity, right? Which apparently is going to be equal to 281.25 joules plus 392. So the work done by Mr. Top Hat is what? Where did I put my calculator? Goodness gracious.
673.25.
673.25 joules. So there's the answer to question 2. All right. Now, all right, so now the question is this. If a constant force, right, is what achieved this motion, what is F naught that made this happen? How should we figure that out? Any ideas?
Divide by, since force is work times distance, wouldn't, or at least in this case, wouldn't you divide by?
Let's see here. You said force, hold on right there. Force is work times distance.
Or sorry, work is force times distance. Sorry.
Yeah, I think you said that. Work is force times distance. If that's true, if the force is constant. Is the force constant? Yeah, we're assuming it's constant. There you go. That's all we need to do. So the work of Mr. Top Hat is equal to the force of Top Hat times the distance in this case, which is 4 meters. So apparently we would want a Mr. Top Hat force of 673.25 joules divided by 4 meters. So what's that give us? 150, 170, no. What's that?
168.318.
There you go. What if you wanted to lift the box in such a way that at the end of the motion, so what if you wanted to lift the box with an essentially, it's kind of a little bit conceptual, the thing I'm about to say. So you want to lift the box such that it starts at rest and it ends at rest, and you've got nearly a constant force all the way up. What force would you lift the box with?
It would be the force of gravity.
Just the force, yeah, exactly. Just the weight of the box is the force you'd lift with. So if you lift with beyond the weight of the box, then you'll have some excess velocity at the top because of the work energy theorem, right? Like suppose you've got a box of cats, right? And you want to lift it, but you also want to like throw it so that it has sufficient velocity to like get to the river, you know? That kind of thing. Sorry.
So what did the cats do to you?
It's not what the cats did to me, it's what the cats mean for society.
Being the best animal?
Being the best animal.
They were worshipped.
Get out of my class. Get out. They were worshipped in Egypt. And where is Egypt now? It's nothing. It's nothing. Think about it. Great ancient pyramids. Yeah. What's Egypt now? Everyone's like, I want to go move to Egypt, said no one. Right? Come on. Wait a minute. Oh no. Now I'm going to be in trouble on the YouTube. All the you gonna report me? Oh man, don't report me. All right, so let us work another problem here. Suppose you have a building and you shoot you shoot a cannon at angle theta, all right? And your velocity of the bullet is v naught. The height of the building is h. My question is, what is the speed of bullet, wait a minute, not bullet, cannonball. I know you thought it was going to be a cat. Cannonball when it hits ground.
So we just do that as V.
Sure, what's VF? We can go with that. Now this one, we're neglecting friction, right? So we can just conserve energy. This was an easier problem. So here we go. We have the initial potential energy is mgh. Remember, we worked this out the other day. The potential energy due to gravity is mass times gravity times height. Now that assumes that the potential energy due to gravity is 0 at ground level. All right, and I'm also assuming that the cannonball is shot from here with velocity v. So maybe whatever. Anyway, so I'm assuming that the initial, when it leaves the barrel and begins the, if you like, make this h. There you go. Feel better? All right. So it leaves the end of the barrel with velocity v naught and height h. Okay. Great. So mgh plus what? Plus 1/2 mv naught squared is the initial energy of the cannonball. What's the final energy of the cannonball?
Just plus or minus half mg of.
Okay,
There's
no.
height, so.
Right, so 0, mg times 0. There's your potential energy. And then what? Plus 1/2 mvf squared, yeah.
We don't have an M.
We don't have an m, and it doesn't matter. So this gives us vf squared is equal to 2gh plus v naught squared. And so we get that the final velocity is the square root of v naught squared plus 2gh. What did we not use? Time? Yeah, there's no time for us. What else?
Mass,
Mass didn't matter? True. What else?
distance.
Distance?
The calculus.
True. Yeah, the calculus is in the details. It's always there. But yeah, well, we've already done the calculus to get to this point. That's true. Fair enough. But theta, that's really what I'm looking for. Theta just doesn't matter. That's kind of interesting, isn't it? It doesn't matter if you shoot the cannonball at this angle, or this angle, or this angle, or stupidly straight up. Right? You shoot the ball straight up, it's still going to hit the ground at the same speed. Now, it'll be in the air different times for those different scenarios, right? So those are genuinely different trajectories, but there you go. So, if we had worked this problem like 3 weeks ago, we would have probably done it a different way, right? This is definitely easier. So, but if you really study it, check this out. Vf squared is equal to v naught squared, right, minus 2g delta y. See this equation right here? Multiply this by m over 2, see what you get. 1/2 m vf squared is equal to 1/2 m v naught squared minus 2g m delta y. Rearranging this, we have 1/2 m vf squared plus m g yf is equal to 1/2 m v naught squared plus m g y naught. Delta y would be yf minus y naught here. So the truth is, it's not really new. The timeless equation was conservation of energy in disguise. It always was. It's just that the only force is conservative, and it's gravity in that scenario. And we can do more now. So let's do that. Let me work a combined concept problem that involves, let's say, a spring and an inclined plane, all right? So example 3. And I'll even throw in a little bit of annoying friction to boot. All right? So we'll put a mass up here. All right. And I'm not even going to tell you the mass, but there's a mass up here. All right. And let us suppose this distance is h. All right. And then over here somewhere, there is a spring. All right, that's attached to a wall. All right. And I guess I could put a cat in the front of the spring. I don't know. No? All right. So the spring, do it. The spring is originally uncompressed. All right. The box slides down the plane, and this is smooth here, so there's no kind of like the box falling over or anything funny there. But let us put in a rough spot, like here, like that. And so this rough spot will have, let's say that this is, a distance of x equals to, I don't know, we'll just say distance x for the sake of this discussion. So there's a distance x where there's a friction, right? So here, this gives you a mu k of 0.8, let's say. Fine, I'll put some numbers in if it makes you guys feel better. Let's say x is 2 meters. Let's say that the height is 100 meters for fun. And we'll give a spring constant k over here of 500 newtons per meter. All right? And then here's the problem. Well, there's various ways to go. Here's some different ways you could play with this problem. One way you could do is you could say the box is given a push at the top of the incline. It's given a push, and it slides down the incline. It goes across the rough spot here, and it compresses this a certain amount, But I think it's more fun to let it start from rest. No. I'm sorry, I'll make up my mind eventually, guys, here. Let's give it a push of V naught of, let's say, I don't know. Well, I'll give you guys the 10 meters per second that you wanted. There you go. You happy? So we give it a push of 10 meters per second. I'm assuming that everything is frictionless except for this rough spot. All right, so it's essentially like an icy plane or something. All right. Like that skating rink over at the mall. I've heard you. No one's gone? There's a mall,
We're engineering students.
You're engineering students?
Yeah, what's please?
Don't you have to woo ladies at some point or no? No? That's down? Oh, okay. All right. So you have been listening to Dr. Sperano. Very good. Let's see here. My main advice is to not overwoo. You have to set the woo low, because you have to think if it works out, then you've got decades, and if you set the bar too high, you're just bound for disappointment later, So,
Is that advice for the girls or the guys? Guys.
I have no understanding of women, so let's see here. Anyway, hey. Look at it this way. I'm married, so you're going to be okay. So let's suppose we give it a push of 10 meters per second and a, what's the word here? Height of 100 meters. And it goes across this rough spot. And then the question is, what's the maximum compression of the spring? So we're assuming that there is enough room for the compression to happen. All right? So that may be quite nonsensical. Maybe, you know what, let me make this a little bit stronger. Let's make this 5,000 Newton meters. There, that should be better. So the question is, when the box comes down here and hits it, right, it's going to compress it a bit. I'll draw the picture scenario up here, right? So it's compressed it a little bit. The question is, like, what is this distance of compression? Let me call that, since I've used x here, let me make this x a d if you guys don't mind. Sorry, I usually use x for the spring.
Sir, I'm running from 10.
Well, you should know by now. So I think it's on you.
It looks so much nicer though.
I'm
That-
good. We're just filled in the middle of the D.
There you go. Oh, okay, cool. All right, so here we go. So the initial energy of the system is what? We have mgh. Oh, I guess I need to tell you m. Let's see here. So what do you guys want the mass to be? 7 kilograms. Great. That'll make it. I'll make the number. Oh, the theta doesn't matter. It actually does. Yeah, I mean, okay. 23 degrees. There you go. It doesn't matter. So, there you go. Is that better? No, that 25 is too much. 25 is too much. So MGH is, but this is not the total energy. The total mechanical energy to start with is what? MGH plus the kinetic energy, which is 1/2 mv naught squared. All right, so let's work that out. We've got our 7 kilograms times 9.8 meters per second squared times 100 meters plus 1/2. Why'd you guys get 7 kilograms? It's so lame. Whatever, 7 kilograms, 10 meters per second squared. All right, what is this mess? What is the total mechanical energy at the start of this? All right, I have one vote for 7,210. Seconded? Okay, well. 7,200, I hope that's right.
What'd you say? Save the check.
We good? All right. So that's how much energy this thing has to start with. And then it comes down here, right? So the final energy is what? Energy final is energy initial what? Minus the work done by friction, right? And see, yeah, I erased it. So let's go here. So the final energy would be 7,210 joules minus what? Minus, what is the force of friction?
U sub k.
Yeah, mu sub k mg here, right? Because there's no kind of funny business. The normal force is just the normal force, it's the weight. So whatever that works out to. So we've got 0.8 times 7 kilograms times 9.8 meters per second squared. And then, so that's that right there is the force of friction, the magnitude of it, right? And then we've got 2 meters, so. So I guess the final energy is the initial energy plus the work done by friction. But that work is negative because it's opposite the direction of motion, right? Friction does a negative work on the mass. So then what? What is that? What's our final energy? 7,100? 0.24 joules. So that's, yeah, we should have made that rough spot like a lot longer to make it more interesting. Oh well. Does that kind of make sense? It almost did nothing, right? It's 2 meters. The thing has gone down 100 meters, and it had a 10 meter per second to start with, right? So like that 2 meter friction part, it's like almost negligible. But there it is, a little bit. We lost 100 joules basically, a little bit more. And so that, guys, in this scenario, that would be the energy the box has like right here. And it would also be the energy it has in the point of maximum compression. So a question I can add to this is, what's the speed of the box right after it goes past the rough spot? Let's find that out. What would that be? So 1/2 m, let me call that Vf squared. That would be equal to 7,100, 0.24 joules. So my Vf in this situation would be 7,100, 0.24 joules times 2 divided by my mass, which was 7 kilograms. And I got to square root that thing. You said 45.04?
Yes, sir.
That's what I got. All right, so, well, that's moving. That's really fast, actually. 0.04 meters per second. I think that's like 100 miles an hour. I don't know. That's pretty fast. Let me just find out. I'm kind of curious. Yeah, how fast is that actually? If I divide by
100 miles per hour, 100.66.
yeah, well, I got 101, but you got to. It's fine. You got a quick conversion factor.
Yes, Siri.
Cool. Siri. We should have asked Alexa. Oh, come on. She's not here. There's a student named Alexa here, but not today. Yeah. See, now I've explained the joke. It's no good anymore, except it'll be hilarious when she comes back. Let's see here. I think I'm working too hard at that joke, but oh well. Where was I? So what's the maximum compression of the spring? So the final energy, right? The final energy, EFF, is equal to 1/2 K, the compression of the spring squared, right? Because the kinetic energy of the spring is, let me put it up here. So what we want to do is set 7,100, 0.24 joules equals to 1/2 kx squared, because so in the end of the motion, when it's fully compressed at this point right here, you'd have like the final velocity is 0. Right? The really final velocity. Okay. And so to figure out the distance it compressed, I'd solve this for x. I'd get x is, like twice 7,100, 0.24 joules divided by k, which I gave you guys to be 5,000 newtons per meter. Square root, right? That's good. The units inside the square root work out to a meter squared. That's comforting. 2 times Siri. How dare you? Let's see here. Divided by 1,000. Square root. Well, this is a big spring. So the spring is compressed. I got 1.685 meters. Yeah. So we're talking about a big spring here, right? Yeah. Now question, what would happen after this? Would be what? The spring would uncompress, and what would happen then? It would push the box back. What would be the initial speed of the box? Probably got a CFOP party he's got to go to. What's that? It'd be, oh, exactly, the 45.04 meters per second. And then what would happen? It would go across the rough spot again, right? How much energy would it lose? Exactly the same amount it did before, right? Because the force of friction is the same, the weight hasn't changed, the distance of the friction spot hasn't changed, so it would again lose that many, right? So what would the energy be on the way back? We could calculate it, right? 7,200, 7,210 minus 7,100.24. So apparently the friction force cost us 109.76 joules, right? So you'd lose another 109.76 joules from our final energy there. You'd have, so coming back here, on the way back, you'd have an energy back of 6990, right? Then the question you could ask is, how far does it go back up the plane? If it's got 6,990 joules at the bottom, how far does it go up?
You would solve for the potential.
So here I'm assuming that the plane extends past the point we pushed it. My picture's not quite right. All right? So if you can imagine the plane extending back like this, all right? Then the question is, how far up would it go? And we can talk, well, so then if you want, we could ask, when you say how far up, you're either talking vertically or you're talking, along the plane. So let's talk vertically because it's easier. So how far vertically? So if you think about it, right? H back, let's call it. It would be what? It gets up here. So it's got the initial V naught, V back, which gives us a E back of, as we figured out, 6990 joules, right? Well, I'm sorry, it's 6990.48 if you want me to be fussy. 6990.5, there you go. I don't even care what the velocity is, all right? The point is, once it gets to the top here, at the final velocity, it would be 0, right? That's as far up as it goes, that's where it gets when it stops, right? So if we figured that out, we would have mg h back is equal to 6990.5 joules. So we could figure out h back is what? 6990.5 joules divided by the mass, which was 7 kilograms, and well, g is still what it is, right? 9.8 meters per second squared. And what would that give us? You said 101.9? Very good. Not joules, but what, meters, right? Now, how far up the plane parallel to the plane does it slide on the way back?
250.5.
How did you get that?
So if you see, like the diagram, instead of
What do you want me to call that?
I just call it C.
Oh, C?
Yeah.
C back?
Yeah.
Sure. And then you said do what?
And then set that equal to sine of 24 equal to the 101.9.
So C back equals to
Sine of 24. Like multiply sine of 24.
sine of 24 degrees times 109?
Divide by 102.
Whoa. Hold on a second.
Sine.
I'm sorry, just a second here. I think you're telling me it, but I'm writing it down wrong.
Okay.
Let me try this again. So it's h back over c back is the sine of 24, right? Because the sine is the ratio of the opposite to the hypotenuse.
Yeah.
So your distance up the plane in the parallel direction, which I've called c back, is h back, which is 101.9 meters, divided by the sine of 24, right? Which you told me is... Cool, got it. 250.5 meters, there we go. Indeed. All right. We haven't done calculus yet today, have we? I feel empty without doing some calculus. I'm just kidding. I'll give you a moment of non-calculus today. We'll get back to the calculus next time, perhaps. Yeah.
Why is the height coming back higher? Shouldn't it have lost energy?
Because it had speed at the start. Because it had this 10 meters per second.
Right, yep.
That's, yeah.
It fell off the end.
Yeah, it would have fallen off the end as I have it originally pictured. You're absolutely right, yeah. Now, of course, you could let it slide back down and see how far the spring is compressed the second time.
And then we do the summation problem to see how many
It-
times it goes back.
Yeah, you could just keep going back and forth and see how many times till it gets stuck on the friction.
We made sure that there's no cracks in the.
There's actually an easier way to figure that out, though. You don't really need to do the full analysis. All you have to do is take your original energy, which was 7,200, and divide by the work, this 100 and whatever it was, 110, right? If you basically take that and divide by that, that gives you how many times you can go across the rough spot before you lose all your energy, right? And so then you just got to think about it. You can't go, I mean, well, anyway, what is it?
65, about 65.4.
What was this difference? It was what, 70, 109? So yeah, we do 7210 divided by 109 point what? 76. That gives me, so 7210 divided by 109.76. Come on, it's marker. I get 65.68. Now, I'd have to, now you got to think about it, right? How's that work? Which, does it stop coming or going? You know what I mean? So like, the first time, the second time, the third time, the fourth time, fifth time, sixth time, seventh time. Yeah, even, so it's odd going this way, it's even going back. It stops on the way back, I think.
Yeah.
About 70% of the way through the rough spot on the way back if we haven't made a round off error. That would be so much more complicated to figure out if we were just using kinematic formulas, right? Goodness gracious.
Is there a cat in the box?
Is there a cat in the box?
There he is. Is it dead or alive?
I don't know. Yeah.
It's showing on this cat. We don't know if it's
Yep.
alive.
Say that it'd be going out again? Because
I wasn't done. We still have 2 minutes. You guys are funny. I'm sorry, but the only thing I can do with a minute is calculus. So here we go. Suppose your force
How much time is left?
is x squared e to the y cosine of z. What's your potential energy? Your potential energy is minus 1/3 x cubed minus e to the y minus sine of z. Because if you take this function and you calculate the gradient of this function, you get that force field. And so if I wanted to calculate, for example, the work done by this force on a path that went from the origin to the point 1, 2, 3, it would be literally u of the origin minus u of 1, 2, 3. So the work done by this force is exactly, 1/3 of 1 plus e to the 2 minus the sine, plus the sine of 3. And, oh, my bad. The 0 gives me something. Minus 1, that's it, yeah. So unless I made a stupid arithmetic mistake, that would be the work done by this conservative force on any path that goes from the origin out here to the point 1, 2, 3. This is actually easier than that. It is, once you understand it. Yeah.
And
Yeah, minus the change in the potential energy. Let me turn off my camera. Thank you to the seafarers for tolerating me. Ah!